We want to be able to take problems like this and create tree diagrams. So we're told an experimental urine test has been developed and it's helpful for identifying a specific disease. We're working with a population that has a high incidence rate for this disease. Specifically, we know and we're told that 12% of this population actually has this disease. We also know of those who have the disease, 84.5 will have a positive urine test. Of those who do not have the disease, 95% will have a negative. So it looks like we are given the specificity and the sensitivity. So this is the sensitivity of the test. And those who do not have the disease, 95% have a negative urine test. This is the specificity. So what we want to be able to do, and what we'll see on the following page, is perhaps calculate the false positive and false negative rates. Or we might want to just know, out of a particular population, what's the probability of testing positive and at all, not necessarily if you have it or don't have it, but just test positive. So let's organize this with a tree diagram. So usually a tree diagram has multiple layers where we're just going to start at the very foundation. And in this particular problem, the foundation is we have a population. So I'm going to draw a person here. And the first thing that we want to think about with this person coming in to take the test, they're going to be arriving to this test and they will either have the disease or not have the disease. And so that's kind of the first branching of this tree. Individuals coming in to take the test. We know that some of them will have the disease and some will not have the disease. And what I'm told is that 12% of the population in this area has this disease. So there's a 12% chance that this individual will be along this branch of the tree, meaning if 12% have it, well then 100 minus 12 will not have it, right? 100% take away 12%, that means there will be 88% of the population that does not have this disease. Now, I want to be clear that we're working with this example that has percentages, and all the information provided to me is given with percentages. There'll be times when you might be told that, there's a probability of 0.12 of selecting someone with this disease. So we could reframe this problem with probabilities, or we might be able to talk about, and what we'll mention in a moment, is this idea of natural frequencies. Meaning if I had a population with let's say 1 million people, and I'm going to change that actually to just 10,000 people. If we had a population of 10,000 people, how many people would we expect to be on each of the branches? So we're going to see that in a moment. But the first thing, again, think about have not. From there, what we want to consider is the result of the test. So of those who have the disease, some of them are going to test positive and some of them are going to test negative. Same thing here. Those who do not have the disease, some of them are going to test positive. That will be a false positive. Some of them are going to test negative, which will be a true negative. Now I'm told in this problem, of the participants with the disease, 84.5% are going to have a positive test. So that means 84.5% of those with the disease are going to test positive, meaning if I have the disease and I come in, then the difference, a 15, if we take 100% minus 84.5%, we see here that 15.5% of those individuals are going to test negative. We can consider the same thing with those who come in and not have the disease. 95% are going to have a negative test. So of those without, 95% of that group are going to test negative. This will be a true result, meaning the difference, the remaining 5%, are going to test positive. So let's consider now this tree. Let's consider we wanted to calculate some percentages and we wanted to create a table, a two-way table. We can use what are called natural frequencies by considering a population of, let's say, 10,000 people. We don't have to do this, but in this particular situation, it can be helpful. So if we have 10,000 people, and out of those 10,000 people, 12% of them are going to have the disease. Well, 12% of 10,000 is, let's put that in our calculator, 10,000 times 0.12, this is 1,200. So we know there are going to be 1,200 people in this population that have the disease. Meaning the remaining individuals, if we take 1,200 away from 10,000, we see that 8,800 of those do not have the disease. And you could have also found that by taking 88% of 10,000. Now let's take this one step further. If 1,200 people come in and those 1,200 people have the disease, 84.5% of that group is going to test positive, and 15.5% of that group is going to test negative. So if I take 1,200 and I find 84.5% of that, let's see what we get. So right here, I'm finding 84.5% of that 1,200, and what I get is 1,014 people. So there are 1,014 people who have the disease and test positive. If I take that away, meaning the remaining, that's 1,014 people out of 1,200. So if I subtract that 10,014, I subtract that from 1,200, what I get, the difference is 186 people. That means 186 people are going to have the disease and test negative. Next, what we know is 5% of the 8,800 people are going to have a positive result. So out of the 8,800 people that do not have the disease, 5% of the 8,800 are going to test positive, which is 440. Meaning the difference, if we consider now those out of the 8,800, that's 8,360 people. Now, in this situation, we have some pretty nice numbers. They're all whole numbers. If we're working with percentages or probabilities that do not have such nice numbers, you're going to want to keep the value unrounded. Meaning you're not going to want to have a whole number. Like let's say we got 10,000 or 1,014.75. We would want to keep it the 0.75. Even though we know we're talking about people, we're going to be most likely calculating some percentages and probabilities. So it's not going to be good if we round in the middle of the problem. We'll want to write the exact value that we see. So let's take a second here to take all this information and turn it into a two-way table, because that is what we've been working with in the past few weeks. So what we know is that there are going to be some people who have the disease, so who have and have not, do not have. So let's write do not have the disease. Some of them are going to test positive, some are going to test negative. We kind of practiced this the last week, where we saw that the total number of people, in this case, if we take this information, there was 10,000 total people. We saw that 12% of them would have the disease. So this is the 1,200. This row here have the disease, so that's a total of 1,200, meaning there's 8,800 here. Now we don't know some of the columns, so we have to fill in the individual cells. Out of the 1,200 people who have the disease, we found that 1,014 are going to test positive, and 186 are going to test negative. Out of the 100 people, so out of this row, out of those individuals, 5% of them, or 440, are going to test positive. That's 440. And 8,360 are going to test negative. We now have some information where we can calculate the total number of people who test positive. So out of these individuals, if I sum 1,014 and 440, I get 1,454. And if I take 186 and I add 8,360, I get 8,546. So now we have the total number of people who have tested positive and the total number of people who have tested negative. Let's take this chart and move it to the next page and answer some questions. We want to be able to calculate some probabilities. And notice we've completed quite a bit of work already. So the first thing that we really need to do is to just frame this and organize this information with a tree diagram. So we have our organized table where we know the number of people that have and do not have, as well as those who test positive and do not. And we want to calculate some probabilities. The first one we want to calculate is what's the probability that a randomly selected individual will have a negative test result. So if I write that in probability notation, this is just the probability that this person has a negative result. We can think of this as a percent as well. What we found based on our first that we made the tree diagram, organize the information in a table, we see that there are a total of 8,546 people who tested negative. That's the total number of people who tested negative out of the total of 10,000. So if we wanted to keep it as a probability in fraction form, this would be appropriate. We know that we can turn this into a decimal. 0.8546 is the decimal probability, which means if I wanted to round this, or make this into a percent, 85.46%. So all of these are the different representations. We could have the fraction form, the decimal form, and as a percent, we see that 85.46% of people have a negative test result. The next thing we want to answer and address is an individual tests positive for the disease. So we know they test positive. What's the probability that they truly have the disease? So in notation that we are familiar with, the conditional probability notation, an individual tests positive for the disease. What is the probability that they truly have the disease? So what we know, given that they test positive, we know that they test positive. What is the probability that they have the disease given that they test positive? So we want to focus our attention on all of those who test positive. So all of those who test positive, out of those individuals, what percent or what fraction of them have the disease? So these have the disease and the test positive. Right, so we saw that when we added up the total number of people who tested positive, there were 1,454 people that tested positive, and out of these individuals, 1,014 actually had the disease. So out of 1,454 people, 1,014 had the disease. So we can turn that, if we wanted to write this as a decimal, we could write this as, I'm going to round this out to a couple places here, 0.6974, which we know as a percent, about 69.74%. So we have our fraction, our decimal representation, and we converted that into a percent. So the probability of selecting, or if this person has a positive result, the probability that they do have the disease is about 0.6974, which means if they test positive, even if they test positive, there's only a 69.74% chance that they actually do have the disease.